uh, which focuses on multimodal waste recognition using vision language model. Slide. So what is EcoVision and what does it do? What is our objective? Our objective is modernizing municipal waste processing through automated high accuracy material identification. So as of now, in most waste processing plants in India, the waste is processed either manually or with semi-automation, which then again also requires a human being to actually interact with the waste. And my objective is to modernize that particular process. The framework that I'm using is a multimodal system integrating grounding dyno for object localization and clip model, which is a vision language model for material classification. So we are using open vocabulary detection to identify waste types without requiring exhaustive task-specific datasets. The innovation here is we are using open vocabulary detection, meaning we don't have to train a particular model again and again every time we see a new type of waste. We are using open vocabulary, which helps the model correlate a particular text embedding with a particular image. So say, for example, you're giving a prompt saying, this is a plastic waste or a crushed plastic. And the model will take the text embedding and it will correlate it with an image of the plastic waste. So that the next time it sees the plastic waste, it'll know that that particular image contains a crushed plastic. And typically, grounding dyno and clip, this synergy is already performing very well. But my innovation and my method of boosting the performance is the implementation of LoRa, which is low rank adaptation. What LoRa does is it fine tunes the final layer of a particular model. And by fine tuning, what I mean by fine tuning? Fine tuning is where I modify just a little bit of weight of the model to better localize with our particular context, the problem. So the problem we are addressing is the inefficiency in waste sorting. Human-led sorting is very slow. It is hazardous, prone to error, especially with hazardous material. Even semi-automated processing also face the same issue. And traditional AI models that uses CNN require thousands, if not millions, of labeled images for every type of plastic and metal and other type of recyclable materials. This makes them rigid. And oftentimes, landfill environments are very cluttered, where traditional models often struggle to classify. And baseline VLMs collapse in chaotic landfill environments. VLMs also have this issue where they do not perform very well under chaotic, cluttered environment. Their predictive accuracy drops sharply when confronted with the heavy occlusion overlapping items and heavily soiled waste typical of conveyor belts, which are what is used in waste processing plants. For example, a standard model might recognize a clean plastic bottle, but fail to identify a crushed, mud-covered container in a pile of debris. And this is what we are trying to solve with our EcoVision model. And the theoretical foundation. So the theoretical foundation is we use VLMs and LoRa adaptation. Our approach relies on vision language synergy, where a vision language model like CLIP, which is a very popular vision language model, which was already trained in millions of data, millions of images and text embeddings. It understands the semantic concept of a material through language rather than just memorizing its visual shape. One thing that we are also trying to do in EcoVision is that instead of classifying materials by what they are, we are trying to classify the materials by what they are made of. Say, for example, you see uh, an organic waste, like banana peel or orange peel in a conveyor belt in a recycling plant. Instead of classifying them as orange peel and banana peel, we are classifying them as organic waste so that we'll be able to use that particular data and recycle them using a different process that is which is not the same as the process that is used for recycling, say, for example, a metal waste or a plastic waste. And it can identify completely unseen objects like a new type of medical waste simply by drawing on its broad, pre-trained understanding without needing a massive new data set. So as I said, CLIP is already trained on millions of images, and we just have to give it particular prompts. Or say, for example, we have the model is seeing an unseen object. We just have to give it a particular prompt, like this is a medical waste. And the next time the model sees the particular image, it will automatically classify it as a medical waste. To adapt this massive model for our specific needs, we use LoRa, adapting only a tiny fraction of its weights instead of computationally expensive process of retraining the entire model. So as I said, we are using low rank adaptation to modify the weights of the CLIP model. So CLIP was mostly trained on clean images, meaning the images that the CLIP has been trained on is very clean, and they usually don't have any cluttered environments or overlapping images. And I used LoRa and a custom field collected dataset to retrain or adapt the CLIP model to our particular context, which is waste recycling plants. For instance, rather than collecting thousands of images to teach the AI what a crushed can looks like from scratch, we use LoRa to simply tweak the model's existing broad knowledge of aluminum. So that is exactly what I just explained. And doing so will allow us to easily recognize the material even in poor lighting and the clutter in landfill. And next, we can go to the architecture. This is the basic architecture of a CLIP model. So as we can see, from the conveyor, the camera will get the live feed, and the image is pre-processed. And grounding dyno is used to detect the bounding boxes of particular objects in the image. And it will also give us crop regions. Both the bounding boxes and crop regions are used by the CLIP vision encoder, and the crop regions are used by the CLIP text encoder. Both these encodings are processed, and the cosine similarity is checked for these embeddings. And if the cosine similarity matches a particular class that has already been trained on, then the particular object will be classified as that particular class. And results and descriptive analysis statistics. So in my testing, under zero-shot testing, the CLIP model achieved 62% accuracy score on TrashNet dataset. So a CLIP model under zero-shot, which is without training for the cluttered environment, and scored an accuracy of 62%. TrashNet is a dataset that is already available in online forums. It is a cluttered dataset, meaning it is not clean. The dataset doesn't have clean objects. The dataset is usually present in the natural environment, say, for example, side of a street. We use that dataset to test the zero-shot capability of the CLIP model, and it scored 62%, which is a very good baseline. And the next point is we implemented a multi-prompting method per class, and this increased the accuracy to 67%. Multi-prompting is when we describe one particular waste with multiple prompts. Multiple prompts being, say, for example, we have a crushed plastic waste. We can describe it as transparent plastic waste, translucent plastic waste, and we can also describe it as a crushed translucent plastic waste. So by doing so, by defining multiple prompts per class, we increased the accuracy from 62% to 67%. Then we applied lower adaptation, low ranking adaptation. We improved the weight of the CLIP model by using the field collected street dataset, and that increased the accuracy from 67% to 70.9%. And then we used multi-object detection evaluation, which is in a particular image, we make the model detect multiple objects, and we then check if the objects detected in the particular image correlate to what they actually are. And with that evaluation, we scored accuracy rate of between 79 to 84%, which is very good. And our hypothesis for after we evaluated are these. Our first hypothesis was that multilayering prompts to describe the various ways an object can appear in a landfill improves the alignment of visual and text embeddings. We proved this by averaging embeddings from multiple prompts per class, as I said, which raised the baseline score to 68%. This is highly practical as it makes the model less sensitive to prompt wording and better at handling generalization, which is different variations like dirty waste, wet waste, or crushed objects in the conveyor belts. Our next hypothesis is that lightweight parameter adaptation, LoRa, can successfully manage the domain shift from clean, pre-trained data to complex, real-world environments. We proved this by adding trainable low-rank matrices to projection layers while keeping the actual model's backbone frozen. This increased the accuracy to 70.9%. And then next, we see the example or my test cases. So the image on the right shows us um, an output from the model before adding the prompts required for classifying organic waste like banana peel. And on the right, we have the same model giving us another output after adding after adding prompts for the banana peel. And as we can see, on the left, we don't have banana peel classified, and on the right, we have the banana peel classified as organic. And discussion. So unlike traditional supervised CNN models, EcoVision requires considerably less annotated data while maintaining highly competitive performance in cluttered scenes. This has been proven by our evaluation and testing. The model demonstrates reliable generalization capabilities, improving the recognition of waste materials without relying on a massive annotated datasets, which was demonstrated by our zero-shot capability and a few-shot capability, which was enabled by LoRa training. The multimodal framework seamlessly integrates with existing mechanical segregation pipelines, making automated waste identification scalable and smart. We can easily implement this model. Since it is very lightweight, we can implement it in the existing conveyor belt systems that are used in recyclable plants and make this scalable. Conclusion and possible next steps. So in conclusion, EcoVision effectively fuses open vocabulary object detection with parameter efficient VLM adaptation, delivering a robust and computationally efficient material recognition framework for real world waste segregation. And for our next steps, we could improve our current model by utilizing hierarchical prompting strategies. Say, for example, we have a few questions that classify or group the objects into particular groups as we progress down the hierarchy. For example, we could ask the object or look into the object and ask the model if the object detected in that particular image is translucent, is it shiny? Then we can ask the next question. If the translucent object looked crushed, or does it look white and does it look like plastic? If so, then it is classified as plastic. If not, then we ask if that particular shiny object is orange in color, or does it look like copper, or does it look like aluminum, or does it look like tin and iron? If so, we can classify that particular shiny object into its relevant class. So that could be one possible next step. And we could also use near infrared spectroscopy to further improve our accuracy while dealing with cluttered objects. So these are the next possible steps in improving the EcoVision model. And these are the references or the top 5 references that I've used. And yes, thank you. Thank you for listening to my presentation. Do we